Hello everyone, and now we are going to be looking at the computer science module for the Introduction to Robotics course. My name is B. Ravindran, and I'm a faculty in the Computer Science Department at IIT Madras. Right? So, during the next few weeks, we'll be looking at various issues that have to do with how robotic systems perceive their environments through sensors, right, and how they act and affect the environment through various actuators, right. Sensors could be, as you have looked at over the course of already, right. The sensors could be things that are from ultrasound, could be infrared, could be cameras, could be more touch sensors, bump sensors. So there are a variety of ways in which the robots look and sense their environment, right. In fact, in some ways, the amount of sensory information that a robot can get is more rich than what a typical human looks at, and it becomes more challenging to operate with this kind of rich sensory information as well, right. And then you have a set of actuators. It could be wheels, right, and as you can see in these humanoid robots, there could be limbs, right, or it could be more articulated mechanical arms like in factory assembly lines. So there are a variety of circumstances under which different kinds of actuators are used, right? And these are typically used to manipulate their environment. So this is one of the core things in robotics, right? There is a system that perceives environment through sensors and then operates and affects the environment through their actuators that are part of the robotic system, right? So what makes a lot of robotics, the algorithmic aspects of robotics challenging is that there is a significant level of uncertainty associated with both of these parts of it, right? There are sensors and there are actuators, and the sensors could be highly unreliable, right? So you cannot say that the robot knows exactly where it is just by looking at the sensory input. Right? There are two reasons for this uncertainty. So one of these reasons is that the sensory information is not complete. So for example, say I'm using an ultrasound sensor, then the ultrasound, let's say I have 8 ultrasound sensors pointing around 8 different directions, right? So in each of those directions, the ultrasound sensor is going to tell me where is my nearest obstacle. Right? But that is usually not enough for me to localize or locate myself within a room. I don't know exactly where I am just because I have this sensory information that is coming into me, right? So the sensory information is incomplete and therefore it is unreliable in that way, right? Another reason it is unreliable is due to a variety of different disturbances or different noise sources that might be there in the environment. The sensor itself, the actual electronics, actual mechanics that goes into the building of the sensor could have some amount of stochasticity, some amount of noise in it, right? Therefore, even though I make the same measurement, I stand in the same place and I measure distances again and again, I might get slightly different distance readings. It's not that it's going to be stable all the time, right? The second thing, there are stochastic disturbances in the environment itself. So I am trying to measure the distance to a wall, and it could very well be that somebody just walks in front of the wall for a brief while, and if I measure the distance exactly at that instant, the distance might be much shorter to the wall than it is actually, right? And I don't really have a mechanism by which I can include all such unmodeled disturbances in the environment, right, and then make decisions out of them, right? So I typically roll them up into what we call noise, right, or stochasticity, and then we try to accommodate for all these disturbances by looking at these kind of noisy model. So, and this is just in figuring out where you are, right? And if anyone has tried anything with robots, right, even trying a simple line following robot, you know that the actuators that are there, even a simple like a gear system that turns wheels, is not completely accurate, right? It's going to take quite a bit of calibration before you figure out, okay, if I say move 1 meter forward or one foot forward, how much does the robot actually move, right? So that is going to take a little effort to figure out. And again, there are many sources of noise, and it could be that that like a gear slips a little bit when you're trying to move, and maybe depending on how much you have lubricated it, things could work slightly differently. And so this the accuracy of this actuators also, if I say do something, whether the robot actually did it, right, is not guaranteed, right? So we have to account for those kinds of inaccuracies, those kinds of noise as well. There is a story that I'd like to tell my class. So we were working with a very simple like a robotic platform, right? So the goal of this platform is that I have a ball in the middle of the platform, and I have multiple degrees of freedom. I can tilt the platform in X, Y, and the opposite directions, right? And the goal is to make sure that the ball stays in the middle of the platform, right? So it turns out that we come up with a very good controller, and then we start executing it, but after a while the controller starts failing. Then it took us we were really confused. What the heck was happening, right? It works fine for a bit, and then suddenly it starts failing. It turned out that the gear assembly that we were using had very high quality plastic gears, right? And after several hours of operation, the plastic gear started wearing, and therefore the controller needed to be adjusted to account for that. And since we were not getting a very accurate feedback, in fact we had no way of measuring the wear on the gear, right? And because we were not able to model that, so even though we had a good controller, it kept failing every so often. And we were able to redesign a controller based on the measurements that we could make, but then that again did not stay stable, right? So there are many such complications that arise, and so what we are going to be looking at through the next few weeks is how to build robotic systems that can robustly handle this kind of noise and uncertainty, right? So I would say that we are going to be looking at what some people call as probabilistic robotics or probabilistic algorithms or robotics, right? And the textbook that is mentioned on the web page is again called Probabilistic Robotics, and it's going to be dealing with these issues in detail, right? So the textbook is very extensive, so I'm not going to be covering the entire book. It's just not possible in the few weeks that we have available to us. So what I would do is I will touch upon these topics. And I'll look at representative approaches for each of these topics, right? In some cases, I'll go in fair detail. In other cases, we will stay at a more higher intuition level, so that you can later on follow up either by reading this book or by doing additional courses that take you in depth, right? So remember, this after all an introduction to robotics course, and we are already packing in a lot of material in this course, right? So the first topic that I look at is what we call recursive state estimation, right? And then under recursive state estimations, we'll look at a variety of different approaches. And so the two main things that I'll be looking at are filters for state estimation based on certain Gaussian assumptions, which we call Gaussian filters. And then we'll also look at one class of non-parametric filters that allows us to go away from making any specific assumptions about the system. And then we'll look at both motion models that model the noise in the motion, as well as sensing models that model the noise in the sensory systems. Again, I'll be looking at very specific examples in both of these, and also try to introduce you to the general principles based on this specific examples, right? And then we'll look at two related problems. One is mapping. Mapping is basically trying to figure out how the environment around you looks like, right? So if you after we look at path planning, I'll also very briefly, I have not put it down here in the roadmap because this is going to be a very brief introduction of learning with robots, right? Learning on robotic platforms. And I'll specifically talk about a paradigm called reinforcement learning, but this will be a very brief introduction to reinforcement learning itself. Okay, right. So the first thing we will start looking at is this problem of recursive state estimation, right? Recursive state estimation is one of the core problems in robotics, right? So if you look at how a robot behaves in its environment, right? You can see that there is a robot here, right? It's in a very complex environment. There are obstacles around it, right? And there are people here who are moving obstacles, and the robot is going to get inputs from all kinds of sensors. You can see a ring of sonars here, and there is a camera on the top, and there are bump sensors. If somebody actually touches at the bot, it will tell you that there is contact, right? And so all of these, right? That's a very rich set of sensory input that is coming into the robot, right? And so with this data, right, so it basically has to figure out, right, so where it is in the world, right? So this is like a world model that the robot has, right? And it has to figure out exactly where in this world model is the bot, right? So so there are obstacles and there are like walls that are modeled, and the robot has to figure out exactly where in this the bot is, and in what direction it is moving, right? At what angle, what orientation it is facing, right? So you have things like the XY coordinates for the bot, right? And the theta, the angle at which it's facing, and the velocity with which it's moving. If it is accelerating, what is the acceleration, and if it has an arm on it, what are the various angles at which the arm is positioned, and so on and so forth, right? And so all of these are information that the robot needs to decide what it is to do next, right? So this information, right? So the information that the robot needs to reliably make decisions about what to do next, right? Or how to behave in this environment, right? So we call these as state information or state variables, right? And sometimes the state information is not directly measurable, as we saw here, right? So I really need to know the XY coordinates of the bot and the orientation it is facing. And even if I have a GPS sensor, because I'm indoors, the GPS sensor is going to be pretty inaccurate, right? It's just going to tell me within a very broad region where I am, and it's not going to tell me exactly where I am in relation to various obstacles or humans and other people that I'm interacting with in the environment, right? And therefore we need a mechanism, right, where we look at all the sensory data, right? Suppose I don't have a GPS data because it's indoors and it's very noisy. I would have to use all kinds of sonar information that I get, right, and as well as any video information, any visual information that I have in order to figure out what my state is, right? So this is a huge challenge. So the recursive state estimation problem looks at this, right? So given all the sensory information I have, right, and a knowledge of what is it that I am doing in the world, right, the sequence of actions that I have tried to take in the world, right, can you tell me what is my exact state right now? So that's the recursive state estimation. It is recursive because I start off with making an estimate for what my state is, right? Then I make an action, and then I make new measurements of my world, right? I make new measurements of where I am. So I have an original estimate of my state, right? So I am in this particular location, right? I'm in this particular location and I am facing north, right? Let's say that is my initial estimate, right? And then I say I'm going to move 3 meters north, right? And then I make another measurement, right? Now I have to figure out where exactly am I, right? Based on my previous estimate, the measurement that I made, and the movement that I made, right? So all of these together helps me re-estimate my state, right? So this is where the recursive part comes in. I use the previous estimate of my state and the action and the new measurements in order to get a second estimate of the state. Right? So this is the recursive state estimation problem, and even if you start off with a very noisy estimate of where you are in the world, right? What exactly is your state? As you do a few iterations of this, you typically end up refining your estimate about your current exact location and orientation and other state variables, and that makes you that allows you to make better and better decisions over time, right? And so move on. Try to make this a little bit more formal in the next few slides, right? And then we'll go to the next lecture for the actual algorithms for estimating this, right? So the state, right, consists of many variables. Here I have marked x0 to xt, which is a history of state here, right? So x0 is a state at time 0, x1 is a state at time 1, and x2 is a state at time 2, all the way to xt, which is a state at time t, right? And so what do each of these x's consist of? Here is an example of things that I already mentioned, a few more here. The first is the robot pose or location in the world, right? The x, y and theta. And if that is more than x, y, I mean, if you can also move in the third dimension, it probably is x, y, z and theta, right? And then you have the configuration of the actuators. So how much has the wheel turned? I mean, if there is any kind of other batteries that could move, any motors that could move, right? So what's the angle of the motors? Or if I'm looking at arms and links in the arms, what are the different relative angles of these limbs of the arms, and so on and so forth, right? So that is another part of the state. Remember, all of these constitute one x, right? So x naught could potentially have many components, x1 could have many components, and so on and so forth, right? And the next category of items that can go into a state description is the object location, the surrounding objects. Okay, where is a table? Is there a table next to me, right? And where is the wall, and so on and so forth. These object locations could be static, in which case sometimes you just represent them as part of the map. But these object locations could also be moving around, in which case you would like to put it as part of your state itself, right? And likewise, not just the locations of the surrounding objects, you could have the velocity as well if the objects are moving, right? So in which case you have to keep continuously updating the location and possibly the velocity of these other objects. And any kind of internal measurements that the robot is making. So things like the internal health of the robot, could be things like battery life, could be things like time to service, right? Could be wear on motors or wear on gears, and so on and so forth. So there are a variety of different things you could think of that essentially would be required for you to make decisions about your behavior in the world, right? So that you're going to accomplish whatever goal it is that you have set out to reach, right? So we would consider in this case, if a state representation is complete, right? If it has all the information that you need for making decisions, and we'll also assume that the state is going to have what we call as the Markov property, right? We'll assume that the state has what we call the Markov property, and this means that the state xt has enough information for me to make decisions, right, without having to worry about everything that went before xt, right? So that means I don't have to worry about x naught, x1 all the way up to xt minus 1 if I know what is xt. Likewise, use, as we will see in the next slide, use correspond to the actions that I take. So I don't have to worry about what are all the past actions I took, as long as I know that I have ended up in state xt, right? And likewise, I don't have to worry about all the past observations, all the measurements, z are the measurements. I don't have to worry about all the past measurements I have made, given that I have ended up in state xt, right? So this we call as the Markov property, right? And so we are going to assume that our states are complete, that they have enough information for us to make decisions, and that our states satisfy the Markov property, so that we don't have to worry about the past, okay? And so making the rest of it formal, so the interaction, right? So we are going to assume that z1 to zt are about the measurement data. So it could be the camera image, it could be ultrasonic sensor outputs, right? Or it could be bump sensor readings, contact sensor readings, it could be wheel encoder readings that tell you how much distance you have traveled, right? It could be tachometer readings that tell you how fast motors are rotating, it could be speedometers, odometers, whatever is the measurement data that you have, all of this could go into one z, right? Likewise, as we saw with the state, z1 is the set of measurements I make at time 1. Z2 is the set of measurements I make at time 2, right? So each one of Z1, Z2 all the way to Zt, each one of this could be a set of measurements, right? And likewise, I'm going to assume that you have a set of control actions that you could do. So it could be moving the wheels of a robot, right? It could be robot motion in whatever mechanism it is. It could be actions about manipulation of objects, or it could be actions that just flex the joint or something like that, right? It could be at some granularity of grasping objects. It could be at the granularity of just flexing joints. There's a variety of things that you could do with respect to these control actions, Okay. So likewise, you have control actions. So U1 to UT. So remember that X denotes the state, Z denotes measurement data, and U denotes the actual action that I take. And each of these set of control actions, U1, U2, etc., could consist of multiple actions that you are doing, right? It could have something to do with the robot motion, right? It could have something to do with manipulation of objects or manipulation of the joint. It could be flexing the joint, or it could be the torque that you supply to motors, right? It could be about grasping an object, or it could be about moving specific joints in a hand, right? And so the actions could be at multiple different granularities, and you don't have to perform all possible action components at every time step, right? So you have the sequence of actions. Again, U1 is the action you took at time 1, U2 is action or set of actions you took at time 2 all the way up to UT, right? So one small notational thing here, I'm going to assume that the first state you start out is x0, right? So you know that you are in x0, then you take action U1, right? And then after that action, you make a measurement Z1, because x0 plus U1 would have moved you to x1, right? So this is how the dynamics is going to be. I start in state x0, right? I'm not making any measurement here. There is some known state, right? Typically, I know some state at x0 that I'm going to start at, or sometimes I don't, but we are not measuring there anything, right? We first make an action, right? And then we move to x1, but I don't know what x1 is. All I get from the robot point of view, all I get is a set of measurements which I call Z1. So from our estimation point of view, the first set of measurements I get are Z1, right? And the first action I have performed is U1, but the state I started out was at x0, right? So Z1 corresponds to measurements made at state x1. Okay, is it clear? So our states notation is going to run from x0 to xt, right? State notation is going to run from x0 to xt, while the action notation will run from U1 to UT, and the measurement notation will also run from Z1 to ZT. Right? And when I want to denote the entire set of measurements, right, x0 to xt, I'll then use this notation, x0 colon t. Or if I say x0 colon t minus 1, that means all the way up till t minus 1, but doesn't include xt. Right? So that's the notation that we'll use. Likewise, just like we did for x, we do that for u and for z as well. Right? And so all of this is fine. Now we have the notations for x, u and z. But then we really need to model the system itself, right? So the stochastic system, in fact, we call this as a dynamical stochastic system of the robot, right, is going to be described by two quantities. So the first I call as the state transition probabilities. The first are the state transition probabilities, right? And then the second set of quantities we are looking at are what are called the measurement probabilities, right? So we have the state transition probabilities and we have the measurement probabilities. So what do the state transition probabilities tell us? The state transition probabilities tell you, okay, given that I have gone through x0 to xt minus 1 already, right? This is all the states that I have already visited, right? 0 to t minus 1. And given that I have taken these actions u1 to ut, right? I have taken actions u1 to ut, and I have made measurements z1 to zt minus 1. Okay, please notice that it's z1 to zt minus 1. These are all the measurements I have made in the past. These are all the actions I have taken, right? And this is the all the states that I have visited. What is the probability that I will be in a specific state xt? Okay, so let's assume that the state xt, the state variable basically measures whether I'm in a particular room or not, right? So if I say in the past I was not in the room and now my action is enter the room, right? Then the probability that I'm in the room now should be very high, right? But there's also some chance that I might not be in the room because the door could be closed, or something could have just stopped me from entering the room, or the door is too narrow, right? Whatever it is, so there must be some small chance. So I can say the probability that I'm in the room given that I was not in the room and I entered the room, is say 0.9 or something like that, right? Now, if you remember the Markov property, the Markov property says that the history is not important. Therefore, the state transition probability that we have becomes something much simpler. Instead of looking at the entire history of states that I have visited, right, and the actions and the observations, I'll only look at the last state I am at, right, xt minus 1. Notice the difference here. Here it was x0 colon t minus 1, which means the entire history from time 0. Here it is only xt minus 1. So that means it's the just preceding state and the action ut. Remember, when I'm in x0, I take u1, I go to x1, right? That's what we thought about, right? So likewise here, so when I'm at t minus 1, I take action ut, so I'll end up in xt. So this state transition probability, right? So this expression, right, tells us, this expression tells us what is the probability I'm going to transition from xt minus 1 to xt when I perform action ut. Right? Assuming the Markov property, this is the state transition probability. So here is one question that you might have, right? Hey, why is it that my zt does not figure in this expression? Why does zt not figure in this expression? Because zt really doesn't cause the transition, right? If I am in xt minus 1, I take ut, I go to xt. I mean, yes, zt is useful for us to estimate what xt should be, but zt does not really cause xt, right? So these state transition probabilities and the measurement probabilities that we are going to talk about next describe the system itself, describe what is actually happening in the system, right? While zt is useful for me to estimate what is happening in the system. So that's the difference, right? So I don't worry about the estimation problem right now. I'm just defining the system equations. Therefore, in the state transition probability, zt doesn't figure in. Okay, is that clear? So state transition probability is probability of xt given xt minus 1 and ut. Okay, so that's what we'll use. We'll assume that things are Markov throughout. Even though we'll go back to the non-Markov case, and then when we are simplifying things, we'll make the assumption of Markov property, and therefore things fall out. Just pointing out to you that most of the development that we'll do for the rest of the course assume that your system is Markov. Okay. So the second component that we spoke about, that we mentioned earlier, right, is a measurement probability. So what is a measurement probability? It is a probability that I will make a specific measurement zt given the history of states, right, x0 to t, the history of actions u1 to ut, and the history of observations z1 to zt minus 1, right. So this is basically my measurement probability. This tells me what is it that I will see, right, once I have gone from x0 to xt, right, and taken actions u1 to ut and made the previous observations z1 to t minus 1, right. So I'm using observations and measurements interchangeably, so bear with me. And so that's basically the measurement probability. That's the second component of our system, right. Assuming that you have the Markov property, we know that the observation that you make at time t depends only on the state at time t. Doesn't depend on what action I did to come to xt. So even ut is no longer relevant for looking at the probability of zt, because ut's impact on zt is only through what xt occurs, right. Once I know what is xt, right, I don't need to know what action brought me to xt, and I certainly don't need to know the previous observations and the previous states and the previous actions I took. So I can simplify the measurement probability significantly into probability of zt given xt. So notice that we have now written out our system dynamics in terms of a state transition probability, which is probability of xt given xt minus 1 and the action you took ut, right, and the measurement probability, which is probability of zt given xt. And we will be repeatedly using both of these system equations in order to derive multiple quantities in the next few lectures. Thank you.